Now it turns out you can represent arbitrary size information using compound data. And that's something we'll do a little bit later this week. But the simplest form of arbitrary size data is lists of values. And so we're going to do lists of values first. Now before I can talk about designing with lists, I have to show you the basic mechanisms that BSL gives us for representing lists. So this is kind of like what happened last week, where first I showed you the define struct mechanism, and then we learned how to design compound data. First I'm going to talk about the BSL primitives for lists, and we'll do that in this video. And then over the next several videos, we'll look at designing with lists. The primitive data that BSL gives us is called lists. Here's the value that BSL gives us for representing empty lists. So that value empty is an empty list of anything you want. It's an empty list of strings, it's an empty list of hockey teams, it's an empty list of numbers. Since it's empty, it can be an empty list of anything. Now let's look at how to make a list that isn't empty. The way we do that is we have a primitive cons, and if I do this, that is a list that's constructed by putting flames onto the front of this list here, which happens to be empty. So this is going to be a list of one element. Here's a list of two elements. And again, the way you read this is it says, well, construct a list in which leafs is the first element and add leafs to the front of. Construct a list in which you add flames to the front of the list empty. So that's a list of two elements. If we run this, Racket shows us the lists using this cons notation, it's called. So it shows us values that look very much like these expressions, but there's an important point to make here. Let me show you a third one of these. Kind of a silly one, except to make this point. If I evaluate this third expression, the value that I get is cons Canucks empty. What happens is when Racket evaluates this, the string append C Canucks produces the string Canucks. And then the resulting value, the resulting list, is the list formed with the string Canucks at the beginning of the list that's empty. So you could put expressions as the operands for cons in expressions. When BSL shows us values, it'll always be formed out of values. Now lists can have more than just strings in them. For example, you could represent problem set quiz grades. And let's suppose we're doing very well on our problem set quizzes, so we've got a 10, a 9, and a 10. There's a list of three elements, the numbers 10, 9, and 10. And we can also make lists out of images, for example. So we could have a list that's a square of size 10 and solid and blue. And let's see, the second element of the list would be a triangle of size 20 that's solid and green and empty. So lists can have all kinds of different values in them. Technically, you can use the list mechanism to make lists that have more than one type of data in them. The mechanism will do that, but our data definitions don't let us talk about that very well. So we're not going to see values like that in this course. Let me clean this up a bit. And what I'm going to do is give some of these values names. So let me call this one L1. And I'll call this one L2. And I'll just get rid of this one, and I'll call this one L3. So now they've all got names. Now that we've made lists of things, we kind of like to know what's in the lists. So Racket gives us two more primitives for doing that. One is called first. So first, given a list, produces the first element of the list. So first of L1 produces flames. First of L2 would produce 10. And first of L3 would produce that square. Okay, so that's first. First produces the first item in the list. First is kind of like a selector. That's because lists are kind of like compound data, right? Cons is basically a compound data constructor saying make a new list in which the first element is this and the rest of the list is the second operand for cons. So first is a selector that produces the first item in the list, and the name of the selector that produces the rest of the elements of the list is called rest. So rest of L1 is going to be empty because everything in the list after flames is empty. And I'll just quickly type these other two. Rest of L2 is cons 9, cons 10 empty. And rest of L3 is cons the triangle empty. So that's first and rest. Those are the BSL primitives for taking lists apart. Now let me ask you a question. Suppose what I want, how do I get the second element of L2? Now, BSL has a primitive called second, and it has one called third. I don't want you to use those. For the next couple weeks, in order to get at the insides of lists, in order to take lists apart, I only want you to use first and rest. So using only first and rest, how do I get at the second element of L2? Well, if I call first as the first thing I do, I'm in trouble, because I'll just get 10. So what I do actually is I take rest of L2. Now that's going to give me cons 9, cons 10 empty. And once I have rest of L2, then the first of that is the second thing in L2. The way to read this is first of rest of L2, so rest of L2 is that. Give me the first of that, which is 9. How do I get the third element? You just do the same trick again. You say first of rest of L2. Now that would get tedious if you wanted to get the 23rd element of a list. And what we'll see starting in the next lecture is that we do it a different way. So let's see, I have cons for constructing lists. I have first and rest for taking lists apart. There's one more primitive that BSL gives me for working with lists, and that's called empty question mark. It's a predicate because its name ends in question mark. And what happens is that empty question mark of empty produces, let me comment these things out so we won't get confused here. Empty question mark of empty produces true. And empty question mark of a list that isn't empty, or in fact of anything at all, produces false. You can also say, if you want, empty question mark of 1, but you're not going to say that as often. We'll often want to know, is the list that we're holding here empty? So there you go. There's the primitives for constructing and operating on lists that are part of the BSL language.